Thank you. Thank you, Harold, for the introduction, and welcome again. What you don't know, what the downside is, of course, of picking this talk is that it is essentially unpracticed, as opposed to all the other ones. Because I've never given it at a big conference, and I had to extend it for today, and I had a conference last week, so you'll see what you will get. I wanted to start out with the title of my talk. First of all, Anastasia asked me again to apologize for the pizza. Apparently, Swedes have a problem when it starts snowing, and that is why the pizza oven broke, they told us. I don't know, the connection was a power outage, apparently. So we learned something today. Even in Sweden, the first snow is challenging. And yeah, we're sorry. And we thank the organizers because they improvised this food on short notice. What I actually wanted to start with is telling you and endear myself to the audience that I love Sweden very much, because I have a very special relationship to Sweden, because about this time of the year, exactly 35 years ago, was the winter of 1989, and I was born in East Berlin. And for some reason, my father could do a research stay at the University of Uppsala. So he was in Uppsala while the wall fell. And the first thing my mother and I did was to go to Uppsala with an overnight train after the wall had fallen. Must have been about this time of year. So Sweden is my image of the West, essentially. I saw Sweden before I saw West Germany. And yeah, and the last time I was here was in June, and I did this swim run thing here in the Baltic Sea, which is also awesome. Okay, but now to more serious matters. ARM assembly. I wanted to write this talk. So this is not a talk of an expert. I am not an expert on ARM assembly. This is the talk of somebody who wrote a talk because he wanted to learn something. Because I was annoyed that I still couldn't read ARM assembly that well when I was mostly doing debugging. So over, let's say, the last 20 years, I had learned to read Intel assembly pretty well. I had hardly ever written assembler code. But ARM assembly was somehow different, and I couldn't really read it. So I wanted to write this talk to learn something, and so again, this is what you're getting. So there might be mistakes in here. So the talk will have two parts. In the first part, I will go over the basics of assembly, so you can understand a very simple piece of C++ code. And then I extended this talk with something I also thought was very interesting and is very different on ARM, and that's the ARM memory model, of course. And I'll try to explain that, and then in the end, we'll also look at some C++ semantics on ARM again and how those two relate. Okay. So without further ado, the goal of this talk is essentially to understand this very simple piece of program. Here on the right, you see how that maps to ARM assembly. I probably don't have to explain and mention Compiler Explorer to this audience. You probably all know this tool. What I didn't know until I wrote this talk is that Compiler Explorer also explains all these assembler instructions when you mouse over them. I didn't know that before. But that turned out to be pretty handy. Okay, so our compiler compiles the code into assembler, well, into machine code, of course. And but the program that our operating system executes is at first doesn't only consist of assembler code, right? So let's start there. What is actually a binary? What's the binary file that your operating system will execute? When I compiled this very simple printf program on macOS for ARM, the resulting file was, I think, a surprising 32 kilobytes. And so I disassembled that and looked at that just to make a slide to explain what's in a binary file. So the linker will produce an executable file, and these executable files have specific formats that are dependent on the operating system. So here you see an executable file for macOS, which is in the so-called Macho executable file format. On Linux, these would be ELF file formats, and on Windows, it's called the PE format. And what this contains at first is a lot of meta information about your executable. So at first, it starts, you see here, there's a little header. Harold asked me not to move that far. Can I move that far? So you see here it starts with some header that has some magic numbers, for example, that tells us this is going to be an ARM executable. It also tells macOS this is actually an executable. I can run this. And then it says what the size of the following meta information is. And here the meta information is only somewhat readable. This describes the memory layout, essentially, of the following executable data. So we have sections here. Some of those sections mention the offsets at which a specific section starts. Some of those sections actually do contain the assembly code we've just compiled. Other sections will contain, for example, constant C strings that were in our source file. So we also tell the operating system where those pointers are. Here's more constant data that will also be in a specific section. So here's our code that mentions the offset at which the executable will find our assembler code. Here's the data segment. And there is these executable formats are documented and also have associated data structures. So this is, for example, the data structure for a segment in this long list of segments on macOS. And here again, you see here would be a name, and here would be where the operating system has to map that segment into the virtual address space. Here is where the data for that segment is in the actual file. Here is what memory protection it should get, etc. So this binary goes on. There's information for the linker. There's information what linker to use. On macOS, every binary has a UUID. It encodes what build this is. We don't really use that, but it's in their source version. This one is important. It tells the operating system what the entry point is for your executable, right? That is not main, of course. The entry point is actually a function in the C runtime that then initializes your global variables, etc., and as a last step calls main. Here you see some shared libraries, and I probably wrote this here. Exactly. So this is what the binary actually looks like, and then afterwards it has a whole bunch of zeros until we find the very little assembler code we actually produced. So this is the assembler code. So assembler is a low-level language. Who here knows assembler code? So I can abbreviate that a little bit. Okay. Who here knows how to write assembler code? Okay, still a few, but now much less. Okay. So assembler is a low-level language. That means each instruction maps pretty directly to a machine instruction. Every line here has a very similar format. First, we have the specific instruction we want to execute, and then we have the operands of this instruction. And these operands, again, take different form. These can be simple registers. These can be immediate values, so that's just a number. These can be memory addresses. This is denoted by the brackets here. So take whatever is in the SP register and add 16 to that, and then give me and then evaluate that as a memory address and give me the value at that memory address. So that's quite a lot to unpack, right, in a very simple instruction. And last but not least, we have labels. So these are essentially addresses in our binary, right? Here, so for example, here we have our constant C string that will be somewhere in our binary. And this is an expression that when the executable is built will be transformed into a pointer, essentially, into a pointer that points inside our own binary. Okay, so now, if you have any questions, by the way, I think you can ask in between, because then we don't have to go back, right? You can just ask whenever something is unclear, or when you think I'm saying something that's very, very wrong. So this is one of the reasons I'm giving this talk, of course. So ARM CPUs have become much more popular, I would say, at least from my point of view. And that's largely due to, well, mobile phones, not only the M1, but also first mobile phones, and now all the Macs that have M1s, Apple M processors. And this is also the reason why I got into this, because our software supports macOS, so now I had to read ARM disassembly. So the first of those, just a little overview of that first generation of those Apple Mac CPUs. They had, I think, 8 execution cores. Each of those cores was running at 3 gigahertz. And what is specific for ARM CPUs and what's different from Intel CPUs is that ARM CPUs have a lot of registers. So here they have 31 64-bit wide registers. These CPUs have, of course, like all CPUs, a level 1 cache and a level 2 cache. And here, I not only wrote their size, but also what a lot of clever people have figured out what their access times is by essentially writing benchmarks and measuring.
Why 31 registers and not 32? Were
They are, I think these are the 31s that you can use. I'm not sure if there isn't the 32nd one that has a special purpose. And it just counts as a 32nd one?
Program counter included there? Or is it?
No, these are all the ones you can use.
What about the link pages?
Sorry?
Link pages?
Could be that is extra. Could be, I did read that and now I forgot about it.
The link registers are part of the 31. The last one is the...
That's right. It's X30, I think, is the link register as well, right?
Yes.
So
And the 32nd is the combined zero register and stack pointer.
We come to that. We come to both of them. I didn't know that they map to essentially 32. Where was I? Yes. So here you see roughly the access times of those pieces of memory. So first, I wanted to look at the registers because that's one of the first things you will notice. So I said there are the 64-bit registers X0 to X30. They have 32-bit equivalents. These are W0 to W30, and these are essentially the bottom bits of those 64-bit registers. You can read the bottom bits and you can write to them, and in that case, the top bits will be zeroed. And there is the special zero register, which doesn't exist on Intel machines either, that you can read and you will always get 0, and you can also write to. And I think that is useful, and I had to Google that. I think that is also sometimes useful when you just want to make some value go away that you don't need. So with only that information, we can already program something very simple. We just need a couple of registers and a couple of instructions, and we can program everybody's favorite programming example, which is the Fibonacci sequence. So that needs very little instructions if you write it by hand. So we have the move instruction. That is the same like on Intel, right? It will move 0 to register X0. So that's our first Fibonacci value. And then we do the same with value 1. And here I store the number of iterations that we want to calculate. So here again, we have a label in assembler that we can later jump to. This is an addition, so we read that right to left. So we add X0 to X1 and store the result in X3. And then we do a little swap here, so we always know what the smaller value and the larger Fibonacci value is. And then so the result is always in X1, I guess. The result will be the bigger one in X1. Here we do subtraction of our counter variable. So again, we subtract 1 from X2 and store the result in X2. Comparison, also very simple, also probably the same as it is on Intel. So here we do an explicit comparison, so we compare X2 to the value 0. And then we do a branch. So the B instruction is always a branch, so that's a jump on Intel, so we're jumping somewhere. And the suffix is the condition we're branching on. So here that would be not equal. So if we are not equal 0, then we will jump back to the beginning of our loop. So that's a very, very simple and probably very efficient implementation of calculating the 7th Fibonacci number. Oh, I had this again as an explanation. Now I did it by hand. And now we can go back to Compiler Explorer and see Well, what happens if we actually program the Fibonacci sequence that way and enable all optimizations? And we see that the result is going to be pretty similar to what we just produced by hand if we compile with optimizations enabled. So here I put this into a simple function and put in some variables, and it made it a for loop, and then the code is the same as before. And now he added a few more assembler instructions. And so we learned some more things about assembler. So here we learned that x0 contains the first function argument. We'll come more to function calling later, but most function arguments are passed in registers. It's also different from Intel, where we don't have that many registers. So x0 will be the first argument. And essentially it does an early out. If it doesn't have to enter that loop at all, then it will immediately jump to the end and exit. And you see down here, x0 is also the return value, because it will now initialize x0 with value 1 and return.
Why does it use the W8X8 register there?
It seems bizarre, right? I don't know. Couldn't tell you. But this was already with optimizations enabled. Seems unnecessary, can't tell you. Okay, and then we assign that to x0. x0 is the return value, and we return. And the rest is pretty much the same like we did now, right? We use the 0 register. 1 is the second Fibonacci number. Then we do an add to calculate the Fibonacci value. We decrement our counter variable. And here you already see something that compilers do because they're clever, that we wrote a for loop that would increment a second counter variable j, and the compiler already figured out that we don't actually need j, that he can just decrement our function argument n instead. But we already heard about compiler optimizations. So that's the same we did by hand. And then he's doing the little moves to switch fib1 and fib2 and do the comparison. Are we done yet? Have we decremented the counter? And then he could just exit. Okay, this is all just a few registers, and we can already calculate Fibonacci values. So registers, we don't have that many. It's still just 31-ish registers. So we need more memory, right? And what's the first memory that we want to use? The
Stack.
The stack, of course, exactly. So we want to use the stack first. The stack per se works like it does on Intel machines as well. So the stack memory is allocated for us by the operating system when the process is started, and the stack pointer variable register is initialized for us, so it will point to the top of the stack. Again, that's the same as it is on Intel machines, and the stack grows downwards. So when we want to allocate a bit of stack memory, this is very fast because we just have to decrement the stack pointer, and now we know that those 4 memory locations there are owned by us. And we can store, for example, the value 0 there at stack pointer plus 8. And when we, yes, so stack allocation is trivial. It's also very fast because that will typically be cached in the level 1 cache, hopefully, because we are always writing to locations that are very close to each other. And when we compile the same little program, the Fibonacci program again, but this time we disable all optimizations, then we see, first of all, that the assembler code is not going to fit anymore on my little slide, but we'll also see that it's using the stack a lot more now. So this is much more inefficient code, but it's much easier to debug, for example, because essentially every single line we have here corresponds to some statements on the right-hand side. So here it will allocate space on the stack for us, and it will, for example, somewhat unnecessarily store our first function argument x0 on the stack instead of reusing the register like he did in the optimized case, right? And then later when he needs it, he will load it again from the stack. So inefficient, but a very simple one-to-one translation. So now we have a bit of memory. We have a few registers. What's like the next important programming language feature that we need to do useful programming? What's the second thing probably in your university book that you do in assembler? Calling a function. Exactly. Calling a function, because now we do have everything that we need to do to call a function. So for that we need the stack again. So we now want to call that Fibonacci function, right? So we again reserve some function on the stack, and now we not only have a stack pointer, but we also reuse one of those registers, x29, to point to the base of our stack. These two are now our frame, right? Our stack frame. So unfortunately, and that's what I found initially makes reading ARM assembler code a bit annoying, is that variable registers like x29 have a special semantics, but they don't have a special name. So they're always used to store the frame pointer, always, mostly always, but they don't get a special name. So it reads kind of, doesn't read as nicely as it does on Intel machines.
What if you want to add like a bigger number? Because it seems like it's 4 bytes, the instruction size, right?
The instruction size is 4 bytes.
If I want to add a number that's bigger than 4 bytes.
We come to one example. We'll come to that in a second, because we have not only I'll come to that. So that's something I haven't mentioned so far. That's also something that's special about the ARM instruction set compared to the Intel instruction set. Every instruction is 32-bit long, and that creates some problems. It creates a problem for adding 64-bit variables, because you can't have a 64-bit immediate value in one instruction. You have to build up that value over a couple of instructions and put it into the register. And on Intel, instructions have variable length. So that makes decoding them much more complicated. But sometimes it would be easier for the assembler programmer, because you can just write a 64-bit integer value into the instruction. So here, back to function calling. This is now semantically the space where we can store our local stack variables, everything between x29 and the stack pointer. Now we want to call the Fibonacci function with function argument 5. So we already know that goes into x0. And now we have the branch and link instruction BL. And that says, okay, yeah, I'm going to jump to the fib function. I have my arguments set up. I want to now execute the fib function. And the link here makes it on Intel a call and not a jump, because the link means we will also remember the return address. And the return address here to our next instruction will be stored in register x30. Again, we are using essentially general purpose registers for a special meaning. And the next instruction would read the return value, which would also be x0. So now what happens inside the function? So execution will jump to that function here. We have our registers set up. Oh yeah, this would be storing the result. Okay, so we want to now execute the fib function, and this is still going to be our state. So we are still pointing to the stack of our caller. And the first thing that our function does, that's our function prologue, which is essentially also the same for every function we're going to call. It is going to allocate its own space on the stack. And then there's a special instruction that is a store of a pair of registers. And that will store both our magic value registers x29 and x30 on our stack. So we can restore them later, of course, right? And x29 was our old base pointer, and x30 is our return address. And now we can fix our own function frame, and now this is going to be the space for our own stack variables. And now the fib function can do its thing. We saw the code for that. And in the end, it will do the exact opposite. There's a load pair instruction, which is the opposite of store pair, that will reinitialize x29 and x30, so the old base pointer and the return address. Then we will release our own stack again, and then the return instruction will jump to whatever is in x30. So that's the function calling semantics on ARM. It's a bit different, so the patterns are all the same. We have, like we have on Intel, we have a little prologue that stores the old information, and then we restore it in the end, but it reads a bit different, and there are a couple of special instructions that we don't know on Intel.
And if I subtract, let's say, 33 from the stack, would it work with an aligned stack? Or
Sorry, what again? Sorry again?
sorry. If I, let's say, at the beginning, I subtract 33 instead of 32,
Yeah.
so the stack is not aligned, would it work?
No, I don't think so. I think on macOS, even so, I'm always more familiar with macOS. I think the alignment requirements are pretty strict. On macOS, they were even stricter. Even on Intel, they had to be 16 byte aligned or something. Even on Intel machines, I think.
I might remember incorrectly, but the addresses here are actually fake. They actually only use the high 30 bytes, the high 30 bits. The lowest 2 bits are more like flags. So every address you jump to and so refer to is 4 bytes aligned.
So it would work, it would just ignore the bits.
Yeah, it wouldn't work because if you try to jump to a non-aligned address, it would the last bits would flag something else, like a different instruction set.
Yeah.
If you jump to a different.
That's not the stack, that's program counter.
Yeah, program counter, if you have a low bits below 4 byte set, you enable fun mode, that's smaller instructions, 16-bit on ARM42.
Okay. Thanks. And I think I wanted to say that our execution continues here. I think that's what I wanted to say here. And so the function calling standard, so here we have an overview of what the registers mean. So we have x0 to x7, that's registers that are used for function arguments. x8 is used for indirect results. Do I remember what that means? I think it means returning a struct that doesn't fit in a register, right? So x9 to x15 means you can use those registers inside your function, and you don't have to remember the old value. It's the caller that has to remember them. x16, x17, x18 are again somewhat special and are reserved. x19, x28 you can use in your function, but you have to save them yourself to the stack. And then x29, x30, we've seen again, are the frame pointer and the link register. Now here I say stack must be 16 byte aligned, apparently. And of course there are similar function calling rules for floating point registers. And these rules are somewhat specific to each operating system, because that's what we call the application binary interface, right? On each operating system, binary code has to be able to call each other, so they all have to follow the same standard. You can look up the rules. On ARM, they are mostly similar. On Intel, for example, there are two very different calling conventions. So the Microsoft Windows calling convention is different from the Unix and macOS calling convention. On ARM, they are mostly similar, but they're not quite the same. But if you're not producing binary code, that's not super relevant to you, right? So now we can go back to our little Hello World example, and we can understand almost all of it. And there's one exception, and what is kind of weird is that part, is where we're only trying to load a pointer to our string. And that needs two instructions, apparently. And that comes back to your earlier question, how do we load things that are bigger than fit in one instruction? How do we load that into a register? And here's how that works for pointers. So we want to calculate, ideally, a 64-bit address, because every pointer could be 64-bit large. But we have 32-bit instructions. Some of that will be used for the actual opcode. So we only have 21 bits for the address. And so what ARM does here to generate, I think, only a 32-bit jump, we're not even calculating 64-bit registers. We need two instructions only to calculate a 32-bit pointer, is it exploits the fact that our memory is split into pages. So we are doing a two-step addressing. First, we're getting the page that our pointer is in. And in the second instruction, we're getting 12 more bits that are the offset inside that page.
But the string there is not stored in code. Text segment is stored in the data segment.
Yeah, exactly. So here's how this works in more detail. So here we have our instruction that gets the that wants to get the page offset. Let's say that instruction is at code address 2000. And what we are calculating now is the page offset of our string, but relative to the instruction we're in. So the result will be that we can access pointers with those two instructions that are 32-bit lower or 32-bit higher than our code. So that actually, so that covers a bit more than only 32 bits, but not 64 bits. Right, so this would be the page offset. The page offset would be 1, the pointer's in the next page, offset with the address of our code. And then the second instruction would add those 8 bytes offset that are the offset inside the page. And then the result would be the correct pointer to our string.
I have a question.
Yes?
Is the page, is that calculated at assembly time or at runtime? Like does the ADR
Since that is, when is that?
It's at runtime. Relative to the program counter. Okay, so our string is offset relative to the program counter.
Are you sure that he doesn't evaluate that when he's calculating when he's building the actual executable?
The start with ADR has an immediate that's relative to the instruction pointer. Okay, and then at runtime it calculates. Yes. Okay, that makes sense.
So yes, you mean so the addition is essentially the calculations at runtime, but the right-hand value will be an immediate value that is the offset, right?
Yes, that would be a 1 in this case.
Yeah, exactly. That's a 1. Yeah. Okay.
Can you work with a page size that is
Sorry?
different? Can you work with a page size that is different than 4K, or is that the only option?
Also a good question. I don't know.
Because on the x86 you have different page sizes.
ADRP is always the value shifted by 12, no matter the page size of
The actual page size. It's just, it does its own calculation, you mean. It doesn't care about any actual page size.
Exactly.
Yeah, exactly.
It doesn't care about the real page size. It just assumes 4K pages for it's just math.
But the chip will support different page sizes.
Yes.
Right, so now we can actually understand that very simple piece of Hello World that covers the essential basics of the function prolog, calling, getting pointers, and returning from functions. Now to the more fun part, even more fun part, memory systems. So ARM implements a different memory architecture than Intel machines. Here's a quote from the ARM documentation. It implements a weakly ordered memory architecture. This architecture permits memory accesses which impose no dependencies to be issued or observed and to complete in a different order from the order that is specified by the program order. And here's an example from the ARM documentation. So here we have, and also an explanation of why that could happen. So here we have a store, and then we have an unrelated load, and another unrelated load. And what the right-hand side will tell us is that this first access here might go into a write buffer that takes so long that these instructions will be done by the time that in the end the write in access 1 is performed. So from an outside observer, it would look like this would finish after these two are finished. So it looks like it reorders the instructions. So here's another example to make this very, very simple. If you have two CPUs and one is assigning a value to two different registers, X and Y, and the other one is doing loads on those two registers, then it's possible, given the ordering of those executions that I've written to the right, that the second CPU would observe all those combinations, all four combinations. Even that one that looks like this is finished before this. Now there are some limitations to this, of course, otherwise it would be impossible to program on ARM CPUs. Now, of course, access to the same bytes must be ordered somehow. Again, from the ARM documentation. So if we would execute those instructions in order, then of course the CPU has to make sure that this load is actually seeing what this store has written. And there are some other restrictions. So there can be address dependencies, right? So here we're loading a value, an address into one register, and then we're storing something at that address. Obviously, those two instructions have to finish in the correct order. And the same here, where we use 1 as the offset. But these are, according to the documentation, the two only limitations. And now we can compare this, just to get some intuition how different this could be and how different it is on Intel architecture, to the Intel documentation. Because the Intel documentation is very, very clear. The Intel documentation tells you loads are not reordered with other loads, stores are not reordered, stores are not reordered with older loads. That means they never look like they're completed before an older load. And the only exception is that loads may be reordered with older stores. So that means this load can complete before a previous store can complete, as long as these access different locations. So, and again, this Intel architecture manual has a lot of very simple examples what this could mean. So here again we have two different CPUs, and what we see here is here I made a little syntax mistake, but we're also assigning 1 to X, and then we're reading X and we're reading Y, and on the other side we're doing this something similar. We are first assigning 1 to Y, and then we're reading Y and we're reading X. And now this tells us that it's possible that this can read 0 and R4 can read 0. Because those two things are not ordered. What did that mean? Why was that allowed? Let me think about that for a second. So this processor will will do what you think it does. It will read 1 here, and here it might read 0 because that thing hasn't completed yet. But that's not true for the same processor. So for the same processor, this guy will of course read a 1 here, and the other processor will read the 1 it has written, but the two values might not see each other. So here we might read the 0, and R4 might also read a 0. But there are transitive dependencies between what processors are allowed to see. So here we have one case that is not allowed that we can unwrap a little bit. So again, we have a simple example. We're reading a 1 here on that. We're writing a 1 on that CPU. We're reading X on the second CPU, and then we're writing Y. And then we're reading Y and reading X in different order. And now it tells us that one specific thing is not allowed. It's not allowed that we read the value of X in R1, and we read the 1 of Y in R2, but then R3 is still 0. Because if we read a 1 here, that means this has executed already. If we read a 1 in R2, that means this has executed already. And these two will be ordered and have to be visible as ordered instructions. So R3 has to read that move as well. So Intel enforces relatively strict ordering relations between all those instructions that are transitive. So all processors kind of have a consistent view of stores automatically. And this results in a total ordering of all stores. So again, we have here one condition that is not allowed that we have to unpack a little bit. So here we are writing a 1 to X, a second processor is writing 2 to X, then we're reading two different values of X, and then we're reading two different values again. So if R1 is reading 1, then this has already executed. Now R2 is reading this value, it's reading 2. Then CPU 4 has to see those in the same order. It's impossible that CPU 4 is reading those two stores in different order from CPU 3. And on ARM, that will be possible. So the Intel architecture makes sure that whenever stores are executed, they are the same for all processors. The order is the same for all processors. So if we go back to our initial ARM example, this means that this combination is not possible on Intel. It's not observable. It cannot happen because it would mean that we see things in a different order on a different CPU. Now here's an interesting fact about the Apple CPUs. Now the Apple ARM processors implement both memory models. And this allows a performance comparison that is otherwise not possible because you have relaxed ARM CPUs and you have Intel CPUs with strict memory order that are otherwise differing in a lot of ways. So there's a nice paper where people exploited that fact to find out what is the cost of that stricter memory model on Intel machines. And they came up with a number. That number is 9%, which is maybe not unexpected, but it's also not an irrelevant number, right? So there is an actual performance gain from the relaxed memory model that ARM CPUs have. 8.94% is the number. Okay, so this relaxed memory model is only observable if you have other CPUs. On the same CPU, everything appears to happen in program order, otherwise programming would be insanely complicated, right? Another interesting fact, if you dig deeper, there's always another level. CPUs try to do execution of those instructions out of order. You find, again, people who try to reverse engineer this because this is not public interface again. So the CPU wants to make sure that for the programmer everything looks to happen in order, but it tries to become faster by executing things out of order as long as you don't see that. And because sometimes they get the prediction wrong, here's a long explanation of how that works on Intel machines. They do a prediction, can I do this load before this store because they're unrelated? And then sometimes it will get it wrong. And it will notice that it gets it wrong, will store that in some hash and remember, I cannot reorder this load before that store. For a software guy, that sounds pretty insanely complicated. And very interesting. Okay, so that's essentially the memory model. And I found it very instructive to look at what the processors actually do in terms of their memory model, in terms of how their instructions work, because that made it much easier, a little bit easier to understand the C++ execution model, right? The C++ execution model is stated in very abstract terms, and these abstract terms make much more sense when you look at the machines that they model than by trying to understand what the standard or the C++ reference have to say about this is a relaxed store, this is a store release operation, etc. Now I wanted to look again at some of the C++ definitions and see how they match to the instructions, actually. So let me switch back to a mirror display. Okay. So the first thing is evaluation order. We used to have sequence points in C++ 11 and before 11. And now we have a complex execution model that still speaks of what operations, in what order operations must be sequenced, but it also allows a multi-threaded execution model. So we have an evaluation order that tells us, for example, in what order that we'll look at the example. I think I wrote it in the comments. Can you may I try to make no? That's good, right? So here I have a very simple little program again. It's just initializing a variable y, and then it's calling a function pointer, and it does a pre-increment and an addition, etc. And now the C++ standard is pretty clear in what order these operations should be sequenced. So this is a full statement. A full statement should be sequenced before the next full statement. For function calls, it's also very clear. Evaluating what to call should be sequenced before evaluating the function arguments. And then, of course, for the pre-increment, we also have a definition that says, well, we increment first before returning the value. And we have more rules. We have the rule that every statement that is inside the function is sequenced after, no, it's formulated the other way around, that everything here is sequenced before the first statement of the actual function body. But this is not necessarily what you see in the assembler output. So here, for example, we see that the 5 assignment doesn't appear at all, right? We don't need that. The optimizer optimized that away. Here we are actually getting the function pointer. Here we are doing the increment. Here we are only completing the calculating what function pointer we need to call. So you see that these actual instructions don't have to follow the C++ evaluation order, because there's this other rule that says that here, I put the quote there, conforming implementations need not copy or emulate the structure of this abstract machine, but are required to emulate only the observable behavior of the abstract machine as explained below. So the compiler is free to rearrange all these instructions that you put in there as long as the result is the same, as long as this difference is not observable. Of course, in the extreme case, he can collapse all these instructions into a constant and say, I return 5. I did all this calculation. I don't need to execute any code. I'll tell you what the result is, as long as there's no difference for you. There are also aliasing rules in C++ that say which pointers are allowed to alias. Here we are. We do see that. So here, very simple function again. We're getting 2 pointers. And now the aliasing rules say that these 2 pointers, since they're both pointers to int, might actually point to the same object. And the compiler has to take that into account. So we're doing 2 assignments, and now I'm returning this value. But the compiler cannot know if we're returning 10 or if we're returning 5 because those 2 pointers alias. And because the compiler cannot know, it has to load this value again before returning it to make sure it gets the correct value, right? We might be able to see, we should be able to see that if I change this to a float and the pointer is not allowed to alias, do we see this? I have another example where we do see this. Sorry? Yeah, do we? Yeah. Yes, oh, the load is gone. Yeah, of course, it's just stores. Yeah, so the load is gone. It knows what to, oh yeah, there's move, there's the instruction I was looking for. So here it says W0, so our return value is just 10. Because the pointers are not allowed to alias. And last but not least, the actual atomic operations, right? So here, I do a store with release semantics, and on ARM that is a specific instruction, which has exactly that instruction, that semantics, store release, and there needs to be a special instruction because otherwise, by default, we would just get a relax store, and that is not strict enough. But if we switch that to let's take that. Let's switch that to trunk, to Clang. Then all we are getting is a simple Intel move instruction, because on Intel the memory model is strict enough that every move satisfies this this memory model, and we don't need any specific instruction, because again we have a total ordering of stores anyway. And I think, yeah, here's the instruction. That was my talk. Thank you very much. Any more questions? I hope somebody learned something. I learned a lot when I did that. Yes?
Yeah, is in your experience a different memory model the biggest hurdle to port code to ARM?
It certainly was a hurdle, yeah. There were cases where we did that wrong, where we maybe just by accident had written something that would have been racy, or was racy on ARM, and it just wasn't on Intel. Yeah, absolutely. We did have those bugs.
Run your code on Intel, then it's not a bug, right? It's correct.
Exactly, it's just correct. And now you have, but in the C++ model, it was always a bug. But in the Intel model, it would just work. And now you run it on ARM, and it will be a bug. So, was that the biggest issue? It was. I think it was a pretty hard to find issue sometimes, right? Because these bugs are hard to find. So yeah, it's the biggest. It's a subtle issue. That's maybe worse.
Do you know if there's any tooling to find these kinds of bugs?
Yeah, all the sanitizers will probably find them. There is the thread sanitizer. I haven't run the thread sanitizer though, but
Valgrind can do it.
yes.
There is a relatively famous TSO x86 TSO formalization for Intel processors. Is there anything like that for ARM?
What's the formalization? What does that mean?
So Intel doesn't give you specific semantics of their memory order, their memory model. They give you a lot of docs, but like not specifically what happens. And there is this famous paper, x86 TSO, which based on a lot of experimentation and also docs, derives a formal model with like model checkers of how it works and like what allows you to do and like what's banned.
Interesting. No, I'm not aware of that. No. I had when I wrote this talk, I had a very impressive interaction with ChatGPT, because for one moment I was confused, and I was confused between the difference between memory ordering, which is just something that another processor can observe, and execution ordering, which in the strictest sense doesn't actually happen, right? It's just the effects that you can observe that are wrongly ordered. So I was looking at ARM disassembler code, and I was trying to see, well, there should be something here making sure this thing is ordered from the perspective of a single processor, right? So that was my misunderstanding. And then I was close to writing a Stack Overflow question to say, why is this assembler code correct? Isn't there some barrier missing or whatever? And then I asked ChatGPT first, and I gave it the ARM disassembler code. And then I wrote a question that was pretty complex that said, given the ARM memory model, given the C++ semantics about this and this and this and this and that, why is that assembler code correct? And then it was giving me a very nuanced, very long answer that told me in pretty much those words that my understanding was almost correct, and I was lacking some nuance in my understanding of the memory model. And they were explaining to me why, of course, execution is not reordered only the observable effects. And that was one of the few cases where I was very impressed with ChatGPT. But there's a lot of ARM documentation online, so if it doesn't get that right, I don't know what it should get right. Okay, any other questions?
Just because you said there's a lot of ARM documentation, but the M1, how much, or M2?
Yeah, so, I mean, not even the processor details are really documented. That's why there are a lot of those reverse engineering efforts to understand what pipelines that has, what execution engines, blah, blah, blah. So I think even things that other vendors would document, Apple doesn't document. I'm not even sure if the size of the level of the caches was documented. Maybe there was also, I'm not sure, maybe it was, but I'm not sure.
And you also mentioned that M1 chips run like an Intel memory model.
Yes, that's how they do emulation so fast. That's super fascinating, yeah, because they have to, like, if those Macs, those new ARM Macs could just execute the old Intel binaries. So they would translate the Intel instructions to ARM and then cache that result. That is relatively the easy part. But the question was, what can they do with the memory model? So what they could have done is just synchronize all memory accesses. And that would have been very expensive. But instead, the M1 CPU has a flag that can switch on total store ordering, I think even on a process basis. And then it just runs like Intel, which is pretty interesting.
Kind of frown upon that say if I'm going to run ARM code from scratch, I should not turn
No.
it on, right?
No. Thank you.